Okay, so let's talk about converting rectangular equations into polar equations. So a rectangular equation is something with an x and a y in it, and these will not necessarily be always like functions that we're familiar with. Now that's a line, and we're pretty familiar with that, and that's a circle. That's actually going to be a circle as well. Oop, this should be equal to 0. But that's not as familiar, not when we square the y. That is like a parabola on its side, and we haven't seen things like this. That's actually a hyperbola. So these aren't all necessarily familiar rectangular equations, okay? But we are going to be able to convert these into polar equations. And one of the nice things about this is some of these rectangular equations are not functions, like circles, hyperbolas, parabolas on their side. Those aren't functions, but you can write the polar equation as you can write it as r as a function of theta, and then we're going to be able to graph those in our calculator, and we're going to see how to do that a little bit later here. Okay, so the idea here with converting these into polar equations is we are going to plug in every time there's an x. Remember, x is equal to r cosine theta, and y is equal to r sine theta. Okay, so we're going to be able to plug in for x r cosine theta, and for y r sine theta. Okay, so let's start by doing that. So we're just plugging these in for x and y. And then what you want to do is you want to be able to solve for r. Okay? So you have r on one side and everything with a theta on the other side. So in what you would do for this is you would factor out that r, and then I would get just 3 cosine theta minus 2 sine theta is equal to 5. So it would look like this. Okay, so what I did is I factored out the r, and then I can divide both sides by this whole expression, and then I get that r is equal to 5, 3 cosine theta minus 2 sine theta. Okay, and so this would be the polar equation for this rectangular equation. So notice that a line is a fairly simple equation, but this polar equation with a sine and cosine in a denominator, this is very confusing. We're not very familiar with this thing at all. So a line is something that is very easy to express and to graph in terms of rectangular coordinates, but not in terms of polar coordinates. Okay? And so it's because rectangular coordinates are straight, you know, they are lines. The graph paper are a grid of lines. But for polar coordinates, the equation is a lot more complicated. Okay? Let's look at another one here. So this is actually a circle here, right? A circle centered at the origin with a radius of 2. Okay, that's the equation of a circle. So we're going to plug in for x, I'm going to plug in r cosine theta. And in for y, I'm going to plug in r sine theta. And I get this. Okay? Now, what I can do here is I can square each of these like that. And now I can what I can do is I can factor the r squared out, and I'm just left with cosine squared plus sine squared theta, and the Pythagorean identity would make that 1, right? So I just get r squared is equal to 4, and so my r, I'm just going to take the square root of both sides, and I'm just going to worry about the positive root when I do this. I get r is equal to 2. So this equation of a circle here simplifies down really, really nice. It's actually r equals 2. And that's actually kind of like the constant function, except, let me show you. So there's no theta. This doesn't depend on theta. So if you take your graph paper for polar coordinates, it would look like this, right? And so this circle is like r equals 1, right? R is equal to 1, and this circle is r is equal to 2, and this circle is r is equal to 3. So these concentric circles are the equation r is equal to a constant. And the idea here is it doesn't matter what the angle is, the distance of each of these points around this circle, it has a length of the distance from the pole to this circle, no matter where you are, what angle you are, is 2. Okay, it is the radius of that circle. So r is like the radius of the circle. So this is a circle with a radius of 2. This would be a circle with a radius of 3. Okay, and so there's no theta there. This is like a constant function where the distance of all the points are a constant distance from the pole. Okay, and this makes sense because you're dealing with these circles. So a circle is going to have a very simple graph, and the math really simplifies down. With rectangular coordinates, it's more complicated, but it's really, really simplified when you're using polar coordinates. Okay, so any circle centered at the origin will have r equals whatever the radius of the circle is. It'll always reduce down to that. Okay, now you know what, the constant function for the rectangular system would be r or y is equal to 5, right? So this would be like 1, 2, 3, 4, 5. This is x and y, and this would be the line y equals 5. So the constant here would be y is equal to, doesn't matter what the x is, y is equal to 5. Now, that's a very simple equation for rectangular coordinates, but it's more complicated for polar coordinates. So to convert this to polar coordinates, in for the y, I would put r sine theta is equal to 5, and then r would equal 5 divided by sine theta, and this would equal to r is equal to 5 cosecant theta. So this very simple function, constant function for rectangular coordinates, is kind of a more complicated function, right? It's r is equal to cosecant theta, or I'm sorry, 5 times cosecant theta. And so this would actually, if you graph this on the calculator, you would actually get the horizontal line, y equals 5. Okay, so these lines that are very simple for rectangular coordinates are complicated for polar coordinates, and then these circles that are pretty complicated for rectangular coordinates are very simple for polar coordinates. That's one of the things you learn. So certain types of graphs are better modeled with using a certain type of coordinate. Okay, so let's try this one here. So for this one here, I'll put in my r cosine in for x, and then r sine in for y. This is equal to 0. Okay, so now this is like r squared cosine theta minus 3r sine theta plus r squared sine squared theta is equal to 0. And I'm sorry, this should have been squared. R squared, you got to square the r and the cosine. Okay, now what I'm going to do here, watch what I do. I'm going to bring these together, and I'm going to move that 3r sign to the other side. And if I do that, I would get this. Okay, and now what I'm going to do is I can bring out the r squared, and I get this again, the Pythagorean identity, and that just becomes 1. So I get r squared is equal to 3r sine theta, and then I can divide both sides by r, and I just get 3 sine theta. Okay, and it ends up that this thing actually ends up becoming a circle that's shifted over, or in this case shifted up on the y-axis. Okay, so let me actually demonstrate that. I'm going to bring this down here. Okay, but I'm going to just move the 3y here, and then I'm gonna end up completing the square like this. So I just brought the 3y over there, and then I'm going to add something, subtract something to complete this square. So what I'm going to add and subtract is half of 3 squared, and so half of 3 would be 3 halves, squared would be 9/4. This would be 9/4. Okay, and so this would move to the other side, and then this thing here would factor into or would condense into this, and this would be this would be the 9/4 on the other side. Okay, so this would be a circle that has a center 0, positive 3 halves, and a radius of 3 halves. And if you look at this, if I draw a graph of this, the center is so 1, 2, 3. So the center is 3 halves. It's like 3 right here, 3 halves, and the radius is 3 halves. So this is a circle that looks like this. So this formula, r is equal to 3 sine theta, is actually a circle that has a diameter of 3 that's up above the y-axis. So if I had r is equal to 10 sine theta, then this would be a circle with a radius of 5. It would have a diameter of 10 and a radius of 5, and it would be up above. And if it were negative 10 sine theta, it would be a circle down here. And if this were 3 cosine theta, it would be a circle like this. If it was negative 3 cosine theta, it would be like this. Okay, and we'll see that when we do some graphs later on. Okay, so it's a lot simpler because we're dealing with a circle, it's pretty complex as a rectangular equation, fairly simple as a polar equation. Okay, and then so this here, this is kind of a parabola. This would end up being a parabola on its side. So let's just plug in r sine theta and r cosine theta. So this would be r squared sine squared theta is equal to 2r cosine theta. I'm going to divide both sides by r, and then I get r sine squared theta is equal to 2 cosine theta, and then r is equal to 2 cosine theta over sine squared theta. And so you would get this equation here, and that should give you a parabola on its side is what it's going to end up being. Let me just tell you, when I looked at your homework, I would plug things in and go and try to solve this and then pick the right choice out, because that way you get experience solving this and trying to get it down to R. The choices are not always solved for R. So on the homework, your choices could be like maybe this step here. They're not necessarily always solving them for R. But usually you want to try, if you can, you want to try to solve it for R, because normally if we can, we like to get our R as a function of theta. And then if you can write it like that, then you can actually plug it into your calculator. And I think this was my last one, or no, I had one more. I had a hyperbola. So let me do that, and then maybe I'll show you how you can plug these into the calculator. So, okay, so this actually we haven't really studied hyperbolas very much, but it's kind of like a circle sorta, except this is being subtracted and not added, and we also have a coefficient there. So if that were being added, that would be a circle, right? If you have a 5 there and a 1 there, that would make it an ellipse if that was being added. Okay, but since it's being subtracted, they call the graph it makes a hyperbola. But basically, to convert this, we're just going to put in our cosine theta in for x minus our sine theta in for y is equal to 4. Okay, so then this would be 5r squared cosine squared theta minus r squared sine squared theta is equal to 4. Okay, well, we'll factor out that r squared, and then I get 5 cosine squared theta minus sine squared theta, and that is equal to 4. Okay, I can't use the Pythagorean identity or anything on there, but I can do r squared is equal to 4 over 5 cosine squared theta minus sine squared theta. And it would look like this. And then I could take the square root of both sides. I'll take the positive square root, and I get r is equal to 2 over square root of 5 cosine squared theta minus sine squared theta. And so I get this weird function like that. So let me actually, with these last two, let's go ahead and I'm going to try to graph these two on a calculator. Okay? So, well, and maybe let me stop there, and I can, we'll bring the graphing calculator in a little bit. Okay, so we'll stop right there, and let me talk a little bit in the next video about how to convert a polar equation back into a rectangular equation.